My name is Enjun from the Hong Kong University of Science and Technology, Guangzhou. Today, I'm excited to present our work, Lecture on Nuance and Pruning Experts for Logic Graph Reasoning. Join me with Siyi Liu and Professor Yongqi Zhang. Here is the outline of my talk. First, I will briefly introduce logic graph reasoning and the limitations of existing approaches. Then I will present our proposed framework, MoKGR, focusing on the mixture of nuance experts and the mixture of pruning experts. After that, I will show experimental results and analysis, including case studies and ablation studies. Finally, I will conclude the talk and discuss the future directions. Let me start with some background. A logic graph stores facts as triplets in form of head, relation, and tail, such as Jack, Watch, Avengers, Endgame. The task of logic graph reasoning is typically formulated as link prediction, given a query, H, R, question mark. We want to infer the correct tail entities that completes the triplets. We consider both transductive and inductive settings. In the transductive settings, the training and test graphs share the same set of entities and relations. But in the inductive settings, we may have new entities or even new relations in the inference time. However, most existing GNN-based KG reasoning models typically have two major limitations. First is rigid query-agnostic path length. Many models use a fixed maximum hope numbers for all queries. As we have recorded in the right table, we have recorded the first right answer entities first appears in the dataset. And you can see that about 34.9% right answer entities appear in the first hope, while about 17.9 answer entities will appear over 5 hopes. So every query is expanded to the same depth regardless of its actual complexity. As a result, some queries are underexplored and others are overexplored, wasting computational and potentially introducing noise. The third one is oversimplified path exploration and pruning. Even when pruning is used, the pruning rules are often uniform and query-agnostic. All paths are treated similarly without distinguishing which paths are truly informative for the current environments or KGs. And the second part is our methods. Here is a high-level overview of MoKGR, and you can look at the left part. Our framework is built on the top of GNN-based path reasoning. We first constructed a relation-directed graph, which is known RD graph, and built a neighbor index so that we can efficiently expand paths around a query entities. On top of this, we introduced two key components, a mixture of nuance experts, which adaptively selects the most suitable path lengths for each queries, and a mixture of pruning experts, which evaluates entities and paths from a complementary scoring, attention, and semantic perspectives to return only the most informative ones. The final prediction is obtained by aggregating the scores from the selected lengths and selected paths. Before introducing our mixture of expert design, let me briefly recap on underlying GNN style path encoding. At layer L, the representation H is updated by aggregating the message from its neighbors. Each neighbor contributes a transformed version of its perspective representations, combined with the H features and weighted by an H-specific attention weights. These methods can significantly reduce computational complexity while improve prediction efficiency. Then is our mixture of nuance and pruning expert framework. When we perform a query, the model first calculates its nuance and selects an appropriate one. Then, through the RD graph, it propagates to the next layer if the pruning experts in that layer is activated. it will be used to prune away irrelevant entities and return only the most accurate ones. And this is the final KG we use for reasoning. So, about the model's detail, given a query, we first compute the contextual embedding CQ to let the model to get the environments to design which experts is most suitable for these queries. Then we will use it to compute the compatibilities of each past length experts, and then use a softmax to compute the length importance. And the final scores will aggregate all the selected length experts. And the second part is mixture of pruning experts. We designed 3 specific pruning experts. The first one is warning experts, which will weigh in the overall importance. And second is attention experts, which will weigh in the local structure importance. And the third one is semantic, which will weigh in the semantic reliance experts. And the third part is training details. The first loss is most common usually loss functions in KGS reasoning, and the third part is importance loss. The second part is importance loss, and third part is load balance loss, which is we have specifically designed to solve the challenge, which means one vendor takes all, which is a common challenge in MOE structures. And the third part is experiments. We have proposed 4 research questions. Q1 is how effective is MoKGR in improving reasoning performance. And the second is how does our expert selection mechanism perform? The third one is how does MoKGR achieve personalized past explorations? And the final one is the ablation studies. We evaluate MoKGR on 6 widely used KG reasoning benchmarks, including FAMLIN, UMLS, WN18RR, and here are the main performance results. You can see that MoKGR achieves the best performance on all datasets in both transductive and inductive settings. And to understand how experts are actually used, we conduct an analysis of expert selection patterns. For length experts, we observe that the model tends to favor a mixture of medium length paths. For example, paths of length 8 are frequently selected at early epochs, but their usage gradually decreases as the gating function learns that shorter paths are sufficient in many cases. The same as pruning experts. We also compare single experts vs fixed weight combinations vs our adaptive weightings. The results show that mixture experts outperform single experts, and adaptive weighting further improve over fixed weightings. We also conduct a case study to visualize personalized path exploration on the family datasets. We plot heat maps of relation type ratios in the selected reasoning paths. For MoKGR, the heat maps clearly show query dependence emphasis. For example, for needs queries, MoKGR naturally focuses more on relations like aunts. We conduct ablation studies to understand the contribution of each component. The experiments show that the balancing terms, the noise terms, and the expert ablations shows all components are important. Finally is our summary. We have proposed a personalized path exploration strategy for KGS reasoning that adapts to query-specific requirements and entity characteristics. We introduced a novel mixture of expert framework, and the incorporating of both adaptive length weighting and personalized pruning strategy will effectively address the critical limitations of fixed path length and uniform path exploration. And the experimental results on both settings show our model achieves the state-of-the-art performance. Finally is In the future work, we plan to establish several guarantees, including optimality and convergence, and improve interoperability for the interplay between NNs and pruning experts. And the third part is scale MoKGR to domain-specific, for example, in the biological KGs or geographic KGs and temporal large KGs, and generalize its experts collaboration to other graph learning tasks. And finally, is bridging MoKGR and large language models for uniform KG reasoning, while MoKGR will provide structural interpretabilities and large language models offer adaptive, contextual-aware generations. Thank you very much for your attention. I'd be happy to take any questions.
If you have a question, just raise the hand, use the mic.
Any questions, you maybe feel free to visit my homepage and drop an email to me. Thank you.